All right, everyone, we are back and we are going to do our full PID control. So proportional, integral, derivative, control. You can also rewrite it like this. So for the full PID, now our closed loop transfer function looks something like this. For our spring mass damper system, we're going to simplify, expand that denominator. It can look something like this. And now we can group those terms. Again, we can see here, third order. So we can find essentially those roots, but we're going to have to do a Ruth table analysis. And there's going to be some interpretation, again, that we can kind of find. So we've already determined, remember, KP is going to increase stiffness, improves arrive time, but increase overshoot. KD is going to increase dampening, reduce overshoot, but improve settling time. KI adds the integrator, eliminates that steady state error, but you can destabilize that system. So we need to have caution when tuning our PID control. There's 3 tunable parameters. And essentially, there's third order dynamics that are introduced by that integrator, so that integral control. So that can introduce basically instability. So be careful of instability, trade-offs, right? And you tune carefully. And we can tune through Routh-Horowitz stability, just like we did previously. So let's go ahead and do it. Let's get at it. So I'm going to go ahead and pull up my Mathematica. We're going to go, why does it keep, I'm going to just click there. There we go. I'm going to go down to PID control now, and we'll get our new transfer function, which looks like this here. We're going to expand this out, and we can see we have our Ruth table, which is 2 again, and now it's 8 plus KD, KP plus 200, and KI. And now we have something that's a little bit more, we have some more parameters that have to be maintained. So first thing we see, KI must be greater than 0. Very important. So that is one constraint, or actually one, we have to hit that. We also see that KD, basically in this example, KD must be what? Can't make that negative, so it needs to be less than 8. So KD must be less than 8. And you can kind of see that moved over here. So KD must be less than 8. So KD must be less than 8. KI has to be greater than 0. And we have this last condition where, so K greater than 0, KD greater than -8 or less than, basically less than 8. And then final relationship right here, we can see kind of how KP needs to be related to all these other parameters as well. So we have bounds on KI, KD, and now KP respectively. So very important, trying to figure out essentially how that's going to work. And you can kind of see, or just kind of manipulate here, if we're going to be stable or not. So if I set, we can actually look at this here. Let's say I set the values KI to 1,000. We can look at this here. If I set right here KI equal to 1,000, actually I'm going to shift enter this. Let's go ahead. We can visualize how this is going to work. We can see it here as well. So if I say KI is 1,000, if I say that my KD is going to be 0.5 and my KP is going to be 0.2, we can see I'm stable. That's greater than 0. It's just great. But in here, I'm not going to be a stable system. And actually, we can see, I wonder if we can find the poles. But we can actually, I want to do that. Let's find, so let's say gs/dot this. GS here, we can say transfer function model, and then we can find I'm just trying to kind of put this in here. I think I have to put the S, comma S, and then, now we're going to do transfer, whoops, one more time, oops, it's not letting me. Transfer function poles, So we can see here, and actually, yep, there it is right there. So we can see we get positive right here. So positive 0.3, positive here, and now we're kind of in trouble. Actually, why is it 1,000? I want to visualize this. 1,000, and then this is 0.2. There, that's better. I was going to say it looked a little weird earlier, but we can see essentially those three poles now. So we're definitely not stable in this, and then we could actually go ahead and see that as well if we look at the response. So if we look at our response, so this was 1,000. What was our Ki is 1,000, Kd was 0.1. I'm gonna actually, sorry for this, but I'm just trying to make it a little bit easier to visualize, because I know that we can set an initial value, like a starting point. Yeah. So I can say Kp. Kp is what? Kp is 0.2. Kp comma 0.2. Close it. Ki was 1,000. This is just setting an initial value, so I don't want to kind of have to swing the parameters each time here, because that's going to get tedious. And Kd, what was Kd? 0.1? Kd 0.5. Ooh, so actually over here. Let's see. 0.2, 0.5. Kd's 0.5. And you see we're unstable. Great. So we can also change again. So let's say, so we need that. Let's just increase. I wonder if we can. Let's put this Kd to, now Kd has to be less than that. Our Kp, let's see if we do it larger. Because the Kd is something I don't want to change. I should have put it up here. Kp, let's do that 10. We're getting better. What about 100? Well, we're stable at least. Let's see what the response looks like. So let's go ahead. So all we're going to do is change Kp to 100. We see now our poles. Oosh. I hope that doesn't change everything. Our poles now are looking okay, right? If we made it even larger, it'd be better. So let's just change Kp to 100. Where's it, Kd? Kp. Yeah, Kp to 100. And look, the system looks stable now. I mean, we can tune it again a little bit nicer for some, different responses, but that's essentially, get out of here. That's effectively what we have to do. So, excellent. Let's go. We found those bounds. You can look at it more generally. And essentially, we can find essentially all of these, bounds on the system. And see, we said this, we already solved this here. And essentially, you can look at the different, system response. We just kind of played around with ours, and we saw when we become unstable, and then you can kind of see where we get out of whack. So these are the takeaways. Remember, Kp shifts the poles for seed, Kd will add dampening, and Ki is going to improve essentially your steady state accuracy. So really, really nice, really good way to ensure stability, and that's your PID controller. Now, we mentioned that this PID is great for, basically, we can use it for known plant models, just like we've done, and we actually just did this already. It's also great for unknown plant models as well. So basically for a lot of these systems, fluids, HVAC, black box systems. So how do we actually empirically tune essentially a PID when we don't know what that plant model is? Well, next time we're going to get into Ziegler-Nichols' ultimate sensitivity method and then also quarter decay method. And that will end our basically PID control lecture. So we'll look at those two techniques for when we can just kind of, how we can tune essentially those parameters, and we'll see you next time. Thanks. Bye.